we will start right now. No need waiting unnecessarily long. Bildschirmfreigabe here. Nummer 3. Okay. So I was thinking that we could take a look more into this nice hooking thingies that we tried last time. Just that this time we will try out the more advanced side of things. So now example we just use have used the remote create thread function call, which is an easy way of injecting code into another process, but of course it has various limitations. And what we can do is now we can try a few other techniques to achieve the same goal. So one thing we can try is to queue a asynchronous procedure call. So maybe let's start with that. And we will make maybe a new project for that. Now we can use the same project. So okay, so we have our target app, which is not doing much. We can for now disable this mechanism that makes it create a child process. And what we need for an asynchronous procedure call to work is we need a some wait function to be active, which is in an alertable state. So we can add here something artificial, like a loop, which just will call in an endless forever sleep x with, let's say, 100 milliseconds, and the alertable flag set to true. This of course is not a realistically useful use case, but there are quite a few calls in Windows that are also alertable, like the various wait for a single object or for multiple object functions. So I think this, just as a demonstration, is fair enough. What we don't have here is really a good way to break this, other than manually, once we are done with the injection, to then manipulate the I variable, but that's an unrelated issue. So we go to our DLL injector. Let's move all the code we have here into a separate function. Right. Checked. Inject create remote thread. We just put the whole. So what do we need? This we keep. We will add the DLL path. Exit path. Where do we have the DLL path here? To our function, so that we can point something. Then we should also create maybe another function. Oops. Disable parallel loading. That's the other thing we taking a look into. Where is it here? So we put this into our function, and we put our injection code into the other function. We need to pass it also the handle to the object. So here there should be fine. It should be const. It doesn't need to be. Why is it complaining? Because we have redefined this. So let's move this out, and here we call our create remote thread. And as said, we are still missing here this one handler hub chance, comma, zack. We need this a few more times. So here and here. Okay, so for now we have just changed haven't changed much. Can now comment this out, create a new function that will be used. We will use then for our other injection method. Wait here. Zack. Okay, so what will we need for that? We have the process open. We need to allocate some memory for the path of the DLL that is similar to what we did here. So we can copy this part. We will also need the address upload library. Zack. Okay. So we wrote the memory. Then we'll need to enumerate the threads that are running within the test process. So let's do that. Handle. I need an include. Which include I need? TL1232. This include has a couple helper functions that can be used to enumerate threads and processes and stuff like that. And it's very common to use those particular includes, since they're quite convenient to use in comparison to just using the native Win32 API. So th32 cs underscore oops what do I need? I need snap thread. Okay, so this pretty much makes an image of the current state of process execution, so that we can then iterate through a consistent list and know that nothing major will change in the meantime. We don't care for error handling, so let's not do that. We will need a for the thread ID. We will need a thread entry 32 for the data that we'll receive. We need to initialize it with size of 32. If we look into the structure, the first field is its own size. The idea is with this strategy that if we ever would have like an extended structure with more fields, then the called API function, just by checking the size passed, can know how many of the fields are available, and it's not necessary to make like new function calls or adding some version parameters or stuff like that. Okay, so let's get the first thread. To first snapshot, reference of our object. Yeah, and we will then run in a loop. So let's make all okay, it's like this. Streckpunkt while okay. So now we can do something with it, and when we need to get the next thread. So now we could do something with the first thread, and before we end the loop, we will want to get the next one. Okay, is equals 32 next. There we pass the same arguments, and if we have iterated through all the threads that are there on the system, then the OK will no longer be OK. We will get an error, and then we break the loop. So here, now we need to check whether the thread belongs to the process that we're interested in, and this we can do by checking the field thread entry punct was it owner process ID. So if this is equals, and here we will also need the process ID, and we add the process ID that we are interested in. We got the process ID in the process infrastructure as well, the full process ID. So we can check if it's the same, and if it is the same, then we can do the thread injection. If not, then we can continue with the next thread in the system. And once we are done, we need to close this handle. Do we need to close something else? No, I think not. Okay, so we have our thread. Then we'll open the thread. So handle gleich open thread, desired access set context, comma false, comma, and thread ID get from here 32 thread ID, and then we can do something here, and once we're done, need to close the handle. Okay, and now we can, once we have the thread opened, we should check actually whether we opened it successfully. So if, okay, just in case, now we can use the QUser APC, and first it wants the address of the function which is to be called. This will be the address of the load library v, so this one, and we need to cast it to the right type so that it can be called actually. So let's do that. APC func, and then we can specify the thread we want it to be injected to, and then we can specify an argument that will be passed to the function. So and this argument will be the memory address where we have written the library path. So it is a different way of invoking the same mechanism as we used in the last time. The last time we created the thread explicitly just for the purpose of loading a library, while here we are trying to hijack an existing thread and make it do our bidding to load the library, and then we're done. Okay, so we do that, we close the handle. Yeah, we don't need anything more. Could print an error message, but we don't care for that. One thing that one would notice at this point is that we are injecting all the threads in the process, which might sound a bit redundant, but since we don't know which ones of them are in a alertable state, it is okay to try to inject in all of them. And once the DLL is injected, additional call to the load library function will just do nothing because the DLL is already loaded. So in this context it is safe. It's not safe in the sense that if we would unload the library later on, so if we would inject a library which only has some short purpose to fulfill and then can be unloaded, if we do that, we would not know whether another thread that at some later point gets into an alertable state, or rather out of an alertable state, would not then again load the library. So we would either need some strategy to mark that when it's loaded it should just do nothing and unload directly, or we just leave it loaded inside the process, which generally for the most code injection use cases is just the way to go. Okay, so this should work. Let's try. So let's rebuild our target app. Okay, let's where we injector. Let's put a breakpoint here. Let's run our code. Okay, something's we need the H process here in the parallel loading as well. Actually, we could disable this. That would be nice. That will give us less threads to deal with, so we will only effectively probably just inject into one. PI punct. Yeah. Okay. Let's roll. Okay, so code injection should be done, or rather in process of being done. Be queued for being done, so to say. Then we put a breakpoint here, and we have to attach to our target process. Attach to process target. Here it is. Attach. Okay. And we should go to our DLL and put a breakpoint somewhere. You already have a breakpoint here. Nice. So let's try running it. Yes. We end up here. It didn't work. It did not work. Apparently it didn't work. Let's see why. We have our target app, images, modules. It did not work. Okay, let's try to debug that. So one thing we can do is let's try with the injector first. Let's first try whether this returns success. So for the head is like this. Let's so if this, then we have printf stdio printf %d \n comma thread id else comma %d comma get last error. Zack. Okay, so let's see, is everything terminated? Then this one is still running, so let's kill it. And let's retry it. What did it say? Good APC. It says it worked, but apparently it didn't. Let's see which path, whether the path is fine. It said it only queued for one thread. 1644. Sorry, 1640 threads. What is the right thread? Why would that fail? Let's terminate everything. Oh wait, we forgot to connect to the process again. That's why we might not have seen whether it worked or not. So for simplicity, let's just add here a message box. Nar, comma, so if we forget to attach to the process, we can still see whether it worked or not. So let's just rerun it again and continue. Nope, it did not work, but it it's here still running. Let's try again. Breakpoint here. DLL path, but the DLL path should be right. This will be the full path. Oh, the DLL path is broken. Why? So we have DLL path, we add hack DLL. But it's apparently definitely not complete. We are missing that. Why would that not do what we want? DLL cut. Oh, sure. I passed the wrong parameter. We need to use here the DLL path. That was a small copy and paste mistake. So let's see, we have one run, okay, a lot of suspended instances. Let's first terminate the old ones. That's the new one with the thread 29 something something. It injected the right thread, and if we run it now, still no success. I tested it before, that was working in another test case quite okay, so I'm not sure why it's now not working that well. Let's just try again and then attach the process. We will see if something is obviously failing. Okay, so this is connected. We can put another breakpoint, one breakpoint here. Hook test, test target up one breakpoint there, run. It resumes. Then we enter our sleepx call. We did it once. Here on the output, nothing happened. Why would that not work as it should? Library has the right address, should be right memory file snapshot. Okay, let's how do we debug that the best way? So we have the process, we have the right path. Now let's first check whether the path is very correct, or let's do a different thing. We can in principle run another so we know when we do the sleepx we will enter the APC if there is any. Let's just make an infinite loop and then step through sleepx and see whether we try to invoke the right library function or if something goes wrong there. Okay, so we have to rebuild the target app. Suck. Apparently one instance is still running. Here. Nope. This Task Explorer tool sometimes locks the debug database, so then you cannot overwrite it. Okay, so we are here. Continue. I'm thinking maybe it's in the alertable state too early. We should, if this does not lead to a solution, we will just start the target application first, and then let it run, and then do the code injection. Okay, so make a step. So now we are outside. Call stack is interesting. So let's see. Load symbols. Did it loaded all of them? No. Load all modules. Loads. Let's restart that once more. To see that is terminated. With the right debug options enabled. Yeah, now we have the symbols loaded. Attach to process. Now, yep. Intermediate. Now we enter our sleep X, and we will step through it and see if we call our library load function or not. Okay. Nope. Until delay execution. So now we execute the system call, and once we return, we should enter a function that serves the APC. We'll see it in the call stack if we enter it. Sleep X. No, we did not. So it did not work. So let's try what I said earlier. We will change it such that we start the process such that it's already doing something, and then we will inject our APC. So the process will be running. We can move this back here. Let's build it. It's possible that during the early process initialization state, the process is getting into an alertable state already, but at that point not everything is set up for the library load library X function to work. So the kernel 32 DLL, which we are using here, is loaded by the intdll, not outright, but after some other things have been prepared. So that might be the reason why this demo is failing. When I tested it earlier, I just tested on a already created process. Okay, so we are running here. We did not connect to anything. So let's see. Let's run it. Terminate the session. Inject on. Before we resume it, let's first attach to it. The scrap debug, attach to process. Then we have one too much. Which one? This one can go. Refresh. Auto refresh. Okay. Okay, so if it works, it should work, and if it doesn't work, we'll have to. Okay, so now we are running in our endless loop. Injected a thread, but it did not. It still didn't load the library. It's still running just around. It says it was successful. I can disable this, but I don't think that this will be the problem. Yeah. Fourth effect. Okay, so again, debug, attach to process. To always terminate the old one. Zack. principle when we are in the DLL main. Sorry, here. No, it was a test target app. It was resumed. Then it runs into this, and this says that it did the injection. So let's see again when we step through it if we run into an APC. We execute and we do the system call, then we exit from the system call. And now at some point, if it works, we should jump to the APC routine. No, but it does not work. That is annoying. It should be working. Did I forgot something? Take the address. That should be the same address. We can try something different. We can try to load the address manually, but I don't think this will have an effect. In my old sample, this is how we loaded the library address, and let's see, and that's the function call half-thread, and this address is the file name that we wrote. Did this work successfully? Okay, next time we should maybe add some more error handling. Okay, so we want to attach again to our target process. Attach, that one will be running in the endless loop, then we can resume it. Then we are here, so write memory was true. Then we get our, then this is running in the loop, we don't care for this, continue. Then we have our loop, we create our thread, at some point we inject the thread, and once we are done we close everything. Okay, let's then in this case I just grab the old demo, copy it into the virtual machine, or actually I have it here. We can try this again. So this is the original demo that we tried to implement, so we use here the open thread and the set APC routine, and then I have a test app. Main. What was it? The main. Here with our sleepx function, and on this it worked fine. So we just start this first. Have a breakpoint in our DLL, and then we run the code that will try to inject it into the existing DLL. That was number 3. We just need to adjust the sample which one it should implement, and the injection in this sample works. I'm not sure why it fails when we do it in the virtual machine. Main. So it should be working, but it isn't. I think the easiest thing to do will be to just try it step by step by copying from the sample all the sorry, that was the wrong project. Copying from the sample, or we can try the same test app. So I don't think we're missing anything in our test app here, because it's still the alertable sleepx. But just to exclude all possibilities, I will just first copy the sample app on the test machine, and we'll try injecting the sample app that I had here before. Okay, so we have a test app running. Just need to find out its PID. Injector. In this case, we of course don't need to create a new process, so we can comment this out. We just have the injection, and here we don't have hproc, so we need to open the process first. So we need only a handful of operations. This one. Okay, let's run it. And our original test DLL is set up such that it will throw a message box on success. But it did not, so something's wrong with our injection DLL. So in that case, let's try the injection DLL from the sample. Even though I don't think there is anything that would be different about it, but let's build it and try with that. Cannot open. I don't think it's a DLL, since when stepping through the function we did not. Actually, that may be even a beta test. Let's just take our DLL, which should throw the message box, and test it with our test app. So we have here our test app. We will run it again. Then we have here the reference implementation of our code injection. Just go to the main file, so then we just need to change the path of what we are injecting. So let's see, RDLL is let's quickly rebuild that. Suck. I will copy it here to the test app folder. Change here the DLL we want it to load. Zack. And let's run it. It says it did something, and it says it loaded it. It did not throw a message box anywhere though, but at least it loaded it. So the problem seems to really be with our injection code. For some reason it does not work as it should. Yes, it threw the message box, just another window monitor. So let's, in that case, just Oops, so that's the virtual machine. I wanted to move this. So let's just for good measure copy the injection code and try it out as is with our DLL. So resume thread we need VPC, process speed, and DLL path. DLL path and process ID. Okay, let's run it. Breakpoint. Debug, attach to process. Target app. This one we don't need anymore. Okay, let's check if we are running within our test code. So this should be called all the time. Now we are seeing another break, so that should be fine. Okay. And this worked. So we have something. We did something wrong in our implementation of the injection code. Let's quickly compare what we might have did wrong. Well, we tried with open process, that did not change anything, so we could one thing to just pass our process here. Wait, CP, what is that? That's just the length. Page read write, page commit, did we page commit, page read write, address, no, that looks the same. Get plus address didn't help. Write plus memory, we also the successfully, where is the default here? We checked the test that was true. Get process address. Yet I don't see any relevant difference. Thread ID, set thread context and false, that's also the way we did it here. VPC address of our virtual memory, that's the same as in the example. Oh, I see the problem. That's embarrassing. We did a copy and paste mistake at at the very beginning. This is not longer valid. We cannot use size of on path, and now we just need to change that. Copy and paste is really the best way to screw something up.
I think there the brackets also missing, or it's plus.
Yeah. And also then this thing is also broken, so let's fix this quickly.
Or is it, sorry, is it white chart string length times size of +1?
Yes.
Or which way around is it? Yeah.
So we need the length +1 times size of which.
Because of the terminating, yes, okay.
Yes, we want the terminating null to be also copied. Yeah, now it should be working just fine. Okay, let's run it now just with our own code, and it works. It showed the message box, so that was a unneededly long detour into copy and paste errors. Yeah, we have now a few instances of this thing running. We should terminate them. Test. Okay, these are all of them. Yes, so the moral from the story: be very careful when copying and pasting. Although it's still strange that we haven't seen entering the function, the library call, when stepping through the things through the sleepx function. But anyhow, so this method worked, and the next method we can try is also similar. So it also uses set thread context, but what it does differently is that there we will target the first thread which we created in the process. So we can comment this out, make it another function. Hijack thread, process DLL path, so this is the same. And we will need, before everything, also the handle of the first thread created, h thread. Okay, so with this p process and pi h thread. So what we will now try to do is to use the set thread context function to change the context of the first created thread, such that instead of executing code from the entry point of the program, it will execute code that we will provide it. So this is a bit more sophisticated, but we have enough time for to do that. Let me quickly dig up my example, which I wrote quite some time ago. This one. So the main difference is with this hijack, or the main practical difference for us with this hijack approach is that we will need to write some code which will be injected into the address space of the process. The previous methods all relied on just using existing mechanisms to redirect execution and then to get the execution back on track automatically. And this is of course convenient, but unfortunately it is not something that works in all the scenarios. So for example, with the APC, with the QAPC method, as I mentioned, you need a thread that will be in a alertable state, and it therefore also is not very suitable if you would want early process execution. So injection during early process execution. It's only good if you want to inject something later on. So what we will need here now for this thread hijacking to work will be some shellcode. Let me quickly check how to do that best. So we can either go with an existing example, or we can write an own one. I would say for starters we will just try doing it using an existing shellcode blob, and then we can look into how such shellcode can be written by hand. So although that's not the most pedagogical way, I don't want it to become too complicated from the get-go. That's the thing. Let's try. I have a simple example somewhere. Let me quickly find that. put that? There should be somewhere. Okay, if I cannot find the easy example, then we'll go with the more complicated one, but I had it somewhere. Yeah, I found it. Okay, so is this the right one with the shellcode? No, that's the wrong one. It's not the simple example. Wurscht, since we don't want to waste time, let's go with the example we have already on hand. So as I said, we will need some shellcode to execute our payload. So let's go with that for starters. So you see in this example, the assembly instructions which we want to execute as comments, and using the online compiler which I showed the last time, we can compile them into individual bytes so that we have the payload ready. And what we see here basically is a function, a small function which saves various registers to a stack. Then we'll have we'll copy the address of the DLL path and the address so the address of the DLL which we want to load and the address of the load library, and execute it. And once it's done with the execution, it will return. And the idea is that it should return the execution to where it was originally interrupted. So to make this work, we will need a process, we need a thread. We again need to open the process, although the process is already open, so this is fine. We will need to again this path. Now we already have the fix in, so we allocate some virtual memory where we write the path the same way that we did last time. We get the address of load library, but now we will need to allocate another block of memory where we will put our shellcode in. So h process, and then here we go with how long is that? Size of sc, this is our code, and we want here this to be executable. Page execute, or was it page execute, not executable? Page execute read write. Okay, and we need a different address sc. Then we copy our shellcode into that location. Since st is just an array, we can use a size of on it. That works. That should work fine. And we'll be needing to modify the shellcode slightly, since we want to set the right value. So here we have these placeholders. We need to replace them with the right values. So we have written a quick check. This order for return address. So we have loaded the library. We have the code. Next, we have two write process. The LL address. We will need some more things. So let's create an array where we the example is not the most straightforward to replicate easily. So we have our address, we have our size, we have saved this, we have allocated the memory, and have written memory. Then then the next step, before we do this, we need first to open the thread that we want to inject into, which is already we should have open already here. So we have this. The thread is suspended, so this is fine. Okay, then we will need to create a structure to get the current context of the thread where its current execution is stored. So text setx, oops, context setx. Then we can read the context using the what was it, get thread context function. Get thread context from our thread, suck. We read it to here. Okay, and now we will change a few things. So first of all, we have the instruction pointer, which tells us where the thread will execute next. There we will set it to the address of our shellcode. The address of our shellcode. Then we need to set the context flag to context control. Then we will need to modify our shellcode. So since we have here these placeholders, we want to write the right values there. We need to save the old value of this first. Suck mem copy. Okay, so sc plus 3 comma reference alt type comma size of return instruction pointer. Then the address, the next thing we want to write would be the address of our DLL, and this we will need, let's just copy it to a size variable. Okay, so path size, suck, it will be the size that we copy. Sorry, not right. We only need the address, so we need this value, and we need just the size of the 64. Okay, and the last thing we need, of course, to set the right position. It will be 31. So we will just count the bytes from the beginning until we are here, and then we know where we how many bytes we need to skip. Then the last thing we need to write is 51. It will be the address of this value here. So the address of our load library function. Okay, then we can write the shellcode to the process. Address sc size of sc, and then we can set the thread context of our thread to the new one. So as you see, we only change one value, really this one, and these flags are just telling the thing later what we will want it to do. So we can change different aspects to the context. We can only change some of the registers. We could change debug registers, change all the registers. So if we pass only context control to the context flags, then we tell it that once we do set a thread context, we only want part of the informations we have received to now be overwritten with the new values, and like the instruction pointer is one of those that will be overwritten. Okay, that we have, and in principle that would be already it. So let's try it. Well, nothing happens, so let's quickly put one pointer here to resume it. There is no test running. Test hook. So test. We don't need a breakpoint here. They'll inject. Here we resume. Okay, let's try. So we do our injection here. Let's put a breakpoint there and save our address for the shellcode. It will be there. Okay. Then this part can be executed. Then we are here. Then we add. Then we connect to our test process. Attach. Then we'll try to. Then if we push play, we end up in the debug break of the new process. Then we can go to the address of our shellcode. What did we wrong? Okay, so we see already first issue. It did not fill in the return address. It filled in here the other offsets, but we screwed something up at the beginning when we wanted to set the instruction pointer as C++, but that looks okay. So let's quickly terminate it, rerun the sample, and see what value we have in old instruction pointer. That might be get thread context. Okay, so this is a problem. If you look in hex, that will probably be just C. So yeah, it's not yet initialized. So what we need to do is we need to let it run for a short while, and then do the injection, such that the thread state is already fully initialized. So let's quickly take a look into our test case. So again, we have just a sleep function, which is fine, and now that should it doesn't need to be the sleep function. It would work with anyone. Let's try again. Oh, we didn't look into the code. Okay, it didn't work. Okay, again, before we resume thread, we attach to the new process. Do we have one or do we have two? We have two again, so let's quickly get rid of the old one. Push, attach. We put the breakpoint here as well. We execute it. We end up in the other breakpoint. We can make it run now. Then we try the code injection, and here we it still doesn't work. Doesn't it initialize anything? It just doesn't read the context age thread. Why is that so? Maybe we need to reopen the thread manually. So hex is turned off, so 16. Sorry, it will be the handle to the thread, it's not the thread ID, and that doesn't help us. Yeah, let's just reopen the reopen it, then it should handle. Did we pass the right handle here? PH thread, yeah. We passed the right thread. So let's instead pass here the thread ID. Oops. Thread ID. And here we open it somewhere here. Handle. Open thread. Desired access. What do we need? We need thread get context. Thread set context. Yeah, that's all we need. Comma first, comma thread ID. So we have our thread. We'll just now rerun it to see whether get thread context will work this time. No. Why would that not work? Did the open function was successful? We opened it. Yes, we opened it with the right context, and then they forgot something. I don't think that's context structure. Oh yes, I forgot something. That's the problem. I need to set this before as well, so let's quickly undo the opening. Suck. I need to set this so that it knows that I want to get the values. Now it should work, I hope, if we have not forgot anything, that is. So we are here, debug, attach to process. Okay, we have quite a few tests which are not needed. Refresh, test, attach, resume. We are in the debug break, then we can resume again. Suck. Okay. At least because there's something. Let's put a breakpoint here and see which values we get this time. So context. No, it didn't work, but interesting. But we set everything as it should, so let's just reopen this source handle, this one, comma source process. That's easier to just reopen it, but this should normally work. I'm not sure why it, because normally when you create a thread, you get all the access on this thread. We can actually quickly test this by keeping breakpoint here, running it. Then we can look into thread. So it's the b null that will be sorry, I need to disable hex display. So 176, and now if we go to our injection app, go to handles, select the type thread, be null, then we see we have full control. So if we have full control, we should be able to get the context, but we do not. Let's try one thing. Let's make it, let's run it after it's resumed, but I don't think this will make a change, to be honest. Suck. Yeah, it still did not load it. I don't think we need debug privileges for that, do we? We might need, but normally just to get the context, that should not be the case. One moment please, so let's, it will be case 6. We might need debug privileges, okay. I thought that worked without this, and that must work without those two. That should work without debug privileges. Yeah, let's just reopen the thread and then see if this solves the issue, but I don't think so. PI punkt David thread ID and did here we should probably terminate everything that we don't need. Thread is equals open thread, set context and get context, comma false, comma data. Okay, let's see again. Sorry. Too fast. Let's see context. Nope, that didn't change anything. Why? Okay, let's just int let's say what Windows tells us which error occurs when we try to get the context of from the process. There is no error, it just doesn't work. And if we ensure that the thread is initialized and it's running, so let's again change the so that the thread is running when we try our code injection. Let's add in a sleep 1000 here. Zack. Okay, error is null, context still not initialized. Context, get context, context control. There is nothing, there is no trick to it. I don't think that yeah, one thing we can try is some of the method needs a so-called debug privilege to be enabled. We can try enabling that, but I don't think that this particular one is necessary, but I might be wrong. So we will do that. Okay, and this time we at least get an error. But okay, shouldn't get an error. It should be working just fine. Let's quickly terminate everything. Let's just run some test app, something that we can. Let's use our own our old test app. This one. So that we at least have a few less complications. So that's the thread. As for the process, we will not create a process then. We'll just try to mess with the existing one. So we need a thread. We need to find a thread. Okay, so for quickliness we will just copy the open function from here. Okay, so we open our function and we need the thread, and we want to open it as well. So I know what the problem might be. Wait, let me quickly try one thing before we go all the way to just randomly trying out things. If the thread is resumed, then we of course need to suspend it again. Suspend thread, resume thread. So we let the thread run for, I don't think we need this. Let's see. We let the thread run for a short while, then we suspend it again, and then we try our manipulation. Still no error, but it still didn't work. Okay, then let's enable the debug privileges. Maybe we really need them. Okay, right now we just get an error. Yeah. Then let's go with. Wait, did we so we want target app. Target app, the test app stays. Okay, so as said, instead of create process, we'll try messing with the existing one just to find out what might be wrong, but I don't see yet what we have messed up. That should have been working just fine. Okay, so we have the thing, then we have to find the thread and open a thread. Oops. Hold under get thread is an own function. We can quickly add it. Okay, so we suspend our thread, we pass our thread, we pass the process, and we resume the thread. And then inside here we should see what happens. So we have our function, error is. Okay, we got another error. Let me try one thing. I will restart the project with admin privileges. That might be just the thing we were missing. Okay. Step. No, still error 6. Damn it. Is our test thing still working? Test. Well, now it's suspended. Terminate. Let's restart it. Test app. Okay, this one is running. We have a new PID. Copy. Run again. Okay, now it worked fine, but it does not return. No matter what we do, the get context call fails. That is strange way. Let me quickly test it again with this. Okay, type 6. Test app is here. Test app. Let's rerun it. Code injection, set thread context. Okay, so we have here our original sample. Here we have our get thread context. We will try to run it. And here, oh, interesting. Is the sample broken? That might have been the problem all along. But I tested it. Let me quickly test it on the host with admin rights again. Zack, we start the test app. So the test app is running. We have restarted with admin rights here, and if we run it now, Zack, step. Okay, so there is something else broken and the sample is just, but it still says injection successful. Interesting. How can that be? That's the problem. Oh, rip. There are only very few fields initialized. The rest is null. So we were maybe unnecessarily debugging a non-existing issue. So let's try just to let it run and ignore. So we already ran this as admin. We can check the error. Yeah, we only want this one breakpoint to see if the old instruction will be valid, and it is. So let's just run it. It didn't work. So let's try something else. So let's undo the changes here. We cannot. So let's go back to creating our process. Have our injection code here. This can go. PE process and pih thread. This we don't need. Zack. Okay, let's rerun it if this works or not. Okay, we have. Yep, this worked. Nice. So let's quickly. Wait. Let's quickly terminate it. It's not running. Okay. So what do we want? We will make the injection code. We want a break. We need a breakpoint here before we resume. Okay, so let's return to our imnet window. So we have here our shellcode address. Very good. We have here our code, and now we try attach to the original process, to our original process. We want to modify target Zack. Okay, so if we now play, then we should fall first into this breakpoint, then we can go to our shellcode at this address, and it's our zeros. Not good. We have some issues still. Let's try again. Terminate test app. Okay, run. So let window clear on. We have the address of our shellcode where it will be. Then we write everything to the shellcode. Before we resume, debug attached to process target. Now we can play. We end up in our bug breakpoint. Okay, we have our shellcode. We can put a breakpoint here and continue. And within the execution we reach the right position, so this is good. We can then inspect this address to see if the path has been written correctly, or maybe we forgot that. Memory 1. Okay, the path is wrong again. We are missing here the DLL, so that's abort. Yeah, that just crashed. Yeah, the same issue. It should be DLL path. Okay, now it should work. Okay, let's remove the breakpoints and be optimistic about it. Should be working. Yep. Nice. Okay, so we run again into a couple demonstration bugs. One thing I want to test now, we are not longer enabling the debug privilege. It's not longer used. And I said I didn't thought we are needing it. I will now restart the project without admin rights, then it should work as well. Let's see if there are any left targets. No, they are not. Hook test. I think the problem might have been from the very beginning. No, well, we had two. First of all, for some reason at the beginning we didn't get this, but probably the next problem really just was the copy paste bug that we already run into once, that we had just the path without the DLL name attached. So if we now just rerun it, it should work without admin rights, and it works. Haha. So let's think, what have we changed? Okay, so one problem was we did not specify this flag when making get control. This was the reason why we didn't get the right instruction pointer. And once this issue was solved, we were just running permanently into the path being wrong, and hence the DLL load not loading properly. Okay. Good. So this much to this example. And what we could now try to do is to write an own shellcode, which will work slightly differently from this one. And to add to it a few more sophisticated functions. So for example, currently everything we have works the way that it always invokes the DLL main function. But what we might want, for example, would be something that allows us to call a selected function within that DLL. So that we not just load it, but that we can call some of the functions inside. And another thing we might want to do is to find a way to not need to use this kernel32 library, but only use exports from the NTDLL itself. So we will try this now. Okay, so we have this, and one function which would be suitable to implement this would be the LTR load DLL function, which is undocumented, but there is this nice site undocumented ntinternals.net. LDR, where is it? Unload. I wanted load, this one. Where it at least gives us the function prototype, so we have a point to start how to use it. So we'll now so for the first part of this part of the exercise, we'll try to write an own shellcode instead of using the ready-made one we just got from another sample, and then within it we will try to use a different function. Let me just check one short thing. Okay, so let's we have that, so we're going to copy it too. Let's make a function here which will just return us a shellcode. So mksc make shellcode, Deutschstern my sc. How much do we need? How large is this? Well, we'll just go with one page for starters. x1 okay, that is not the best approach, since we need the length further down. So let's call it write sc, write shellcode. It will take a process handle, and that's it. And it will just write the whole shellcode to a process. So it will do the allocate part, and here we will have our own shellcode. So let's call it byte. Oops, my sc. Let's make it large enough. It's no problem if it's too big. And at the very end, we will just write it. It's already then in the middle. We will use the helper that we already used. Where was it? Here. That allows us nicely to write individual bytes. So p byte is equals my shellcode. To do. So here's our to do. So this. Okay, we will need the path of the DLL, so let's stern del path address, and right shellcode will receive our process and the DLL path, sorry, and the address of the DLL. One thing we will also need to pass to it will be the return address. Let's think how to do that best. Yeah, let's do it here. Void asterisk return address. So we can comment this and this out. Right address, return address will be the comma, and it will return the memory, this one. We can improve that later on. Okay, so void st, so here we can what type does this have? .64, so let's cast it to the right type. Okay, so we write the path to the memory of the process. We have the address where we want it to be. We communicate to our shellcode writer the address and the function. Sorry, the address and the return code. Then we have here our process to which we'll be writing, and now we need our shellcode. So let's work on that. We will need a data area, so something where we can where we can store data to. Okay, so this will return the address we want to jump to, but internally it will not be the same, so we need another address for that. Void asterisk is equals this, we will set later. We will return entry. Let's make a definition. Define space will be minus code .pbase. Oops, code didn't copy. Code .pb minus the initial address, so that sc. So this will give us the relative address from the current position to the code base. So this will give us the why is it complaining? Open, open, close, close, that should be fine. Define base, Abstand. Yeah. Okay, so one thing we want to store into our code block will be qpq++. the address where we actually want to go. So this thingy, be our first parameter. That will be our first slot. Then the next address will be the address of the function that we want to call to load our library. So for now we will just go with this method of obtaining the address. We can change this later, but we need the different address, so we go here with ntdll dll ldr, how was that called? Did we need the right capitalization? And we're missing one. No, here. Zack. So we have the address. So the next thing, code.pq plus is equals. Now this method of obtaining addresses is contingent on our process having the same architecture as the process we are trying to inject code into. If we would try to inject code into a process of a different architecture, then the addresses of course would be wrong and this wouldn't work. But as we said the last time, this is a special case which we will not be looking into. The only thing we want is for now to make this work as easy as we can for one given architecture. We will later want to have here also the address of getPros address, but for now it should be fine the way it is. Okay, so we will now proceed with our entry point. So the entry point will be now the address here, Zack. And if we later add here more entries, just our entry point will be shifted further down within the whole thing. So it would be good for testing to start with a breakpoint. Not xcc. It was in try. And at this point we could already try running this thingy just for giggles. I will try again this automatic attachment to new processes, because that is very helpful if it really works. Okay, so we have here our hijack thread, we have here the data, we have the path, and we resume it. So if we run it, we should now end up simply in this breakpoint. Where do we put it? In this breakpoint. And then we will continue writing the rest of our shellcode. One assembly instruction at a time. Okay, so here we are. Didn't it attach? In principle, at this point, we should be attached. Debug, attached to process. Yeah, we should be attached. So now if we run, okay, we enter here and refresh. So something is not right yet. Let's see. We have the sure, that is not valid. We need of course address relative to SC, so we need SC plus code SC my SC minus my entry, because that is a stupid mistake. Okay, wait, one more thing. This one should be byte 10 byte asterisk. This one as well. Let's just cast everything to byte asterisk so that this works correctly. My SC. Wait, my SC should be already of the right type. My entry. Let's just go with byte asterisk here. Then we save on a cast. And address is a void that needs to be in brackets. Doesn't that work with arrays? That should work with arrays. Why doesn't this work? Normally you can just subtract and you will get the right offset. Okay, it wanted the additional brackets. Apparently it was not clear enough to it. Or maybe it would have compiled and just the IntelliSense was off. So what we forgot to do is we when we here calculate the position where we want to have our entry point, we use the address within our address space, but the address within the address space of the target application is of course a different one, and this is why this crashed. So now if we just add a relative offset to the address base in the other process, that should bring us to the right memory location. Let's run. Okay, so we are in this breakpoint and zack. That failed again. Let's try. Let's see why. Byte SC. Let's put a breakpoint. My SC. Sorry, that is wrong. Entry is further down the line. This one. This way it should be correct. Zack. Okay, that's the low-level breakpoint, and now we are in our breakpoint. Perfect. It worked. So since we don't have much except our own breakpoint, there is nothing much happening here. We can of course just add a few more breakpoints so that we see that it's really our own code. Here we have the address. So this is also fine. We don't need this breakpoint since everything's working. And here, as you wait, is that our code, or did we just randomly arrive at the right position? Oh, that should be B. It was our code. It just was padded with 0 since we wrote the wrong type. Okay, now we are here and we have our far too many breakpoints. Why do we have so many breakpoints? We only wrote a couple of them. Let's add some knobs here. I just want to make sure that we have the right offset. CC is also what you have when you have uninitialized code, so probably we should just initialize this with 0. Then we should see now our 4 breakpoints and a couple of knobs, and then just everything padded with zeros. Yep, so we have our breakpoints, then we have our knobs, and then we have a lot of zeros. So this is working. We will leave the breakpoint in for a later debugging, since that will help us. And what do we want to do next? So first thing would be to save all the registers. That would be a good thing to do. Does this work? That should be working. Let's quickly find our online assembler. That's the wrong one. This one. I like this one. Okay, so we have a instruction that will save all the floating point registers onto the stack. this is quite nice since it's just one instruction. Unfortunately, we cannot do the same for the integer registers in 64-bit case, so we will add, as you have seen here, for example, we have here the same push for the floating point registers, and then manually all the push instructions for the relevant registers which we want, but we want to be smart about this, so here we make a loop. Int e is equal 0, e is smaller null xf, since that's how many registers we have, strich I++, and we will need to make one case for continue for the 4th register. If e is equals this, then continue. Okay, that's the wrong equals. So the 4th register would be the stack pointer, and obviously we don't want to save the stack pointer register. So okay, and now we need our loop to write the right jump in the right instruction, so we can copy this code block here just for reference, and we will see that some of the instructions are easy to copy as to store, like the RCX DX up to here. They're just 1 byte, but the other ones unfortunately are 2 bytes, so you will need to have a differentiation what we are doing. So if I is smaller 1, 2, 3, 4, smaller equals 7, smaller 7, wait, shouldn't we start at 1? No, we should not. But is this 4 then correct? 1, 2, 3, 4. We skip 4. We should start at 1. And then go down to, I think, like this. Okay, so if this is less or equals 7, then the instruction we push will be 50 plus. Okay, that would be more elegant if we go with this notation. And that should be for, we'll see. So 50 1 plus I, and if I is 4, then 5. No, that is not wrong. So this, which way do we want to do that? Push RCX. Let's start with 1. Oh, wait a second. I think we are missing one of the push instructions here. Let's quickly look into the disassembler. If we go with RAX, will it be 50 0? Oops, wait. Zack. Yeah, push RAX would be 50. So we could save RAX as well, so why not? So we start with 0. 4. We will keep 4, so that is fine this way. Okay, yeah, that makes sense. So we're missing here. I mean, RAX is usually not relevant, since it is always, not always, but often just used as a scratch register and often changed. But now it should work. So 0, 1, 2, 3, 4 we skip, 5, 6, 7. So then we save those. I mean, the more, actually we probably should do it like this, since while plus works, technically what we want, we have a opcode, then we want to push only a section, and we should here probably make and null x 7 to ensure that I mean we are only going through this value range, but just for correctness let's do it this way. Else now we have the other registers, the ones that have 2 instructions. So first we push the 41 instruction, and then we can actually, that will be easier, we can stick with this, and if this is greater 7 then we first push 31 and then we start again at 0. So if this continues counting but we end it with 0, then it will then cut the one set higher byte, and we should end up with the right code. So let's try it. Let's run it and see. So push rax rcx rdx rbx p d, then 1 9 8 9 10 11 12 13 14. Yep, I think this these are all of them. Wait, are they debug Windows registers? No, there's a 15 one we did not add an instruction for R15, and this one, yeah, 7. So this is equal lower equals, I think, yeah, now it should work perfectly. I'm not sure if we will be in time today, since I only have half an hour more time, and there are quite a few things to do. Would you be okay with extending the lecture a bit, since we wasted some time at the beginning?
Yes, no problem.
Okay, perfect. Okay, so now we have our complete register saving. So let's write here what we are doing. Okay, so we have saved our registers. Now we can start manipulating them. So let's allocate some stack space. That will be, what will it be? Sub rsp, comma 38 bytes assemble. Okay, then we did one start annotation. Okay, so this will add hex 38 bytes, so that's in integer. Let's see how much that's in integer. So breakpoint Ansicht für Programmierer hex 56 bytes on the stack. So let's copy this quickly. And we can put this in one line. So this will be a double word is equals 0x 38 0c 8348, and we write down what this should be. Zack. Okay, so we have is D the right one? Yeah, the D is the right one. So we have our stack space. This we don't care. Okay, so now we will call our load library function. So the way function calls work in x64 Intel is that the first 4 arguments are passed as registers RCX, RDX, R8 and R9, and the rest of the arguments would be passed on the stack. But since our function only takes 4 arguments, we are good to go without any additional without requiring any additional stack space. So the first thing we would want to do is we would want load. Let's start with the last one. So we know from other sources that the first two arguments can be null, so let's clear them. Move rdx, so let's have the first one, rcx0 and rdx, oops, rcx, rcx dx 0 and 0, so this we can quickly assemble. Zack. So this will be this, and rdx will be this one. As you see, technically only one position changed here. We can break it up like this. So we will do it by first writing a single word v is equals null x c748. Then we'll write a byte c1, and then we can write a double word which is just 0, and then we can repeat this, and then just we change here this to 2. This one with rcx rdx. Yeah. So we have here our two registers. The next thing we want to do is here will be to fill the module file name. So this will be that complicates things. This is supposed to be a Unicode string, not a well, a Unicode string is a special structure which we'll need to allocate. It looks like this. So it's a type of strings that Windows uses internally, and it's not null terminated. Instead, it has a length which tells you how many bytes are there, plus a buffer length in case you want to pass an empty string and then allow something to write to it. That complicates things. It complicates things a lot. It complicates things a lot, but we can make it work. We will just put it somewhere in here, the whole string, since we have as much place as we want to do. Okay, so let's see the definition of the string again. Okay, we close it. Yeah. So let's grab this, write it down. We have an address of this, but then we will need the length of it as well. So let's just pass the DLL path instead and move this into our function, to our right shellcode function as well. Okay, so we have a DLL path which is written somewhere. Then why is it completely okay? Because of this can go. Okay, then we will know the length, because we can just make a VCS lang on this, and we have the address. Let's call it DLL DLL path, oops, and path size we already have. Then we have everything we need. So the first one is a short. Short is a word, so it's a length, but the length is in okay, it's the right unit. It's in individual bytes, not in count of characters, but the length should not contain the terminating one. So let's just change this path length. Path length is just this, and path size is this +1. That gives us the same result. Okay, so here we have our length. Maximum length is plus will basically be the size. Okay, so oops, copy paste fail. Then here we have a pointer. So this structure, the way it will be implemented, so this will have the offset 0. This will have the offset 2, but this will not have the offset 4, but it will have the offset 8 because of memory alignment reasons. So there will be like a dummy variable here with the offset 4, and it will have the size of 4. So we can quickly demonstrate this. Const int a is equals field offset. What was the first argument? Field offset again. Field offset. Somehow the intelligence will be broken. It shows it here. So type is this. This field is length. So here we see. If it's a constant, it's evaluated in real time, it's 0. Max length, let's call that B, will be 2. And if we look for buffer, C, it should be 8. And it's 8. So, can get rid of this. Now we add a double word. We just shift by D since it's 0 anyways, or we can explicitly write 0 to it. And then we have our keyword. Q is equals, and this will be the address DL path. This one. Long 64. Long. Why is it complaining? Because of a typo. So here we have now the whole structure. So we want the memory address of this thingy. Which, let's see how to get that the easiest place. With address, wait, we made a small mistake. We wanted something else to have here as well, namely this address anyway. Okay, so hashtag define offset. Let's call the first red offset. This one is just at position 0. The next offset will be the LLD load library, load DLL, loader load DLL. That will be at offset 8. The next one will be our address, our Unicode string, so path 16, and the whole thing is How big is the whole thing? The whole thing is 16 large, so the next one would be 32. Okay, just in case we need it. Zack. So ideally, if we make base plus offset, it should give us the right position relative to the instruction pointer. Let's try it. So here, when we call the function, we will want to load an address. So let's assemble that. Load address into register R8. Let me think. Is that what we want? Path offset. I think. So RIP plus null x. Just write some pattern that is easy to recognize. R8, then R pattern. So let's assemble it. Okay, the pattern needs to be something smaller. Let's start with no 8. Oops. 7 7. Okay, so we have here our next instruction. So here we can make a space. This will be our offset, and this is our code to be written. We can use the same methods here. 8D for C, D for C, and 05, 05, and then we write the word which I think should be path offset plus base. Path offset plus base, since this is negative. Yep. And the last thing we want, or the last thing we need, will be a address where the code will return the module base of the loaded DLL. So when we look into our documentation, we have here in the pointer to a handle. So we'll add here another keyword. This will be for later, which is just 0 for now, and this will be then the at offset 32. Oh, that's wrong. That's just a previous definition. So we will call it hash define module offset. Let's make this look nice. Zack, zack. Okay. So in principle it's the same thing, just with a different offset. So we here change it to R9. Assemble. As you see here, only it changed from C to D. Sorry, from 05 to D. Zack. Abstand. It was R9. We can take the same code, just we need to here 0D, and here we said it's module offset. Let's check documentation once more. We want the address where we write to, and here we want the address of a Unicode string. Yep, that should be right. So we have prepared our function call with the relevant arguments. So now we can invoke the function. So what we will want to do will be call rib minus something annual XFF AABBCCDD. One too much. So this is here now our call function, a function call, suck. We add this. Bam, bam, bam. Where did my pattern went? 8, 4, 3, and the 7, 7 went away. Okay, let's go with 0, 0, BBCCDD. Okay, let's try with 0. Okay, 0. Because I have a minus there. That's why plus yeah, it's fine, it's fine. It was just the minus screwed it up slightly. I wanted to change it to a plus. Suck. CP. Yeah, it's too long. The CC will be cut, but no, wait. 1, 2, 3, 4. No, the length was right. 7, 7. Yes, CC stuff. It's fine, everything's fine. Okay, so this is easy. We only write 2, 15 FF, and then our double what? And this time we go for this one. Yes. Okay, and at this point the loading would be done. What we are still missing is, of course, continuing the execution from where we started, but that would already be a big step. So let's add here a breakpoint and try the code if it does what we want it to do. Okay, something's not compiling. Redefinition DLL path. Damn it. Remote DLL path. Copy into remote DLL path, DLL path, remote DLL path. Yep. Okay. One more bug. Yep. Okay, so we are in the breakpoint, and we have here our instructions, and we have here our stack preparations. We set those two to 0, we set those two to something, and before we do the call, put a breakpoint, and now we can inspect our variables. So our R9 is a void asterisk. Right. So R9 should be pointing to somewhere here. 2, 4. Wait, did we set this to 0? We set this to 0 with a Q. That should be fine. So we should have here somewhere zeros. Let's start probably here. Then we have here a few zeros. It says 24. 24 is here. 1, 2, 3, 4. Okay, something we have not done right with the offsets. Pim. Let's quickly think again. So this one is this one starts at 0, this one is 8, then here we have at this position we have 16 plus 8. 16 plus 8 is 24, not 32. And this one, wait, the path offset 0. We want the let's write down the let's write down the address, the positions at which we end. So we start at 0, then we have here 8, then we have here 16. After those three we have 24. After this we have 32. Okay, and after this one, since it's plus 8, we have 40. Oops, just 40. Wait, so these offsets are right: 0, 8, 16, 32. Okay, so here again we load R9 with our module offset 32 and base. And base is basically code begin. That might be wrong, let's think about that. So SC is the very start, and this does not change. And the code, this part, will change and it will move. So whenever we increment it, this will change. So then we have a larger number minus a smaller number. It should be right. Okay, let's try again. Maybe it was right, we just thought it's not right. Okay, so we are at our breakpoint. Let's compare the memory contents. We should use a memory window for that, not the other ones. Put this here. So we start at this offset. Stack memory. So I want to have 16 per column, so the first one is the address. So the first one is the return address, the second one is the load library address. Looks plausible. Then we have our length and size, which is also plausible. Then we have our dummy padding, and here at this address we have our pointer to the string. So let's check this out. So this one would be 8. Okay, there's no that is, but this is wrong. It doesn't work. Let's quickly check. So memory address. Wait. Sorry. 8 is wrong. No, it should be right. We have 16 per column, so in the middle it should be 8. So at this position, does it tell me where I am? No, it doesn't. But this address, okay, it's the same address, so we want to read from this. Let's say it's a 64 asterisk at this address, and then it says CC. Okay, this cannot be valid. Let's stop it. Let's check a breakpoint here. What is our DL remote path? So this is the address clear all we expect to be written into the memory. and it should be, and we are advancing it by the right type. So let's continue and once more. Yes, we are here. Memory check again. Suck. Thanks. Okay, this is already one bug. Somehow this is not written properly. But the entry point. So the entry point is fine. So the writing as such works. For some reason we just don't write the top. So we write address as C size. This should be fine. That's weird, and that is really weird. Well, the first two things, they look right, so let's just go with the start address here. Wait, that's not the start address. Okay, so this is the start address. We x4. Genau. Okay, so x4 point asterisk, and then this +8. Like, why don't I get the same value? I should get... I must write void. Okay, so this one works, and this one is the thread start routine. Okay, so the first two are fine. Then we have our string where the lengths look plausible, and then from here we should have the address of the string, but this is not fine. It is just plain wrong. Code, but we don't overwrite this anywhere either. We just progress with the ++ all the time. Okay, let's check whether what we are writing is actually correct. Maybe we have some strange bug here, and that's the address. We want mysc. Nope, here what we're writing is fine. This is correct. And then if we write it, size of mysc should be fine. Continue. And we get to our breakpoint. And then if we look into the memory, okay, well, we get a different position each time we try it. Oh, now it's fine. Okay. Weird. So let's try +8. What did we say? So +8 plus this address +8. This should be did it just change? No, it's fine. Okay, so where were we? Expect this to be a wchar, and the position 20 +8. Nope, it changed. mess up something with the offsets? Oh yes, we messed up something with offsets. Well, this is the address where we are writing to. So we have 1, 2. Again this one, and that's the offset. So this was fine all the time. I was just looking on the wrong row. Okay. So zack over here. So we have this part probably looking fine. Then we have here zeros, and CC is our breakpoint instruction. So that is fine. So if we look on the right row, that should be this one plus 8. Didn't seem to work. Wait, where are we? I see we are still at the wrong position, so let's run the code till we arrive in our shellcode. Let's clear this. Memory, so we need the address, zack, where does it start here? Okay, so we need this address plus 8. It points to an, did we use the right value? Remove the URL path. That should be the right, but apparently somehow the address is wrong. Oops. Damn it. Yeah, this should be the address. So 10 plus 8. Let's go with so this is our address. If we go here, then we there's and at this address. So if we interpret this as a, we should have the string, but we don't. So if we go there, sorry, we then, wait, I forgot one asterisk. Yeah. Okay, so that was working fine as well. Okay. Then let's set the breakpoint here. Play. Shit. I set it in the wrong row. We wanted to set it once higher. I think something is still not quite right. Okay, so we set it here. Play. Clear. Okay, so yeah, if we look on this, it's 13. That does not look right. So if we go here in the memory window, null x. So just a recapitulation. We wanted this address 10 to be in the first and the address 20 to be in the second entry, but we are by 4 too far out. So we need to subtract 4 from the value which we are feeding in. Okay, let's wait, but is it correct? We subtract 4. Why would that be 4? Because nothing here has a size of 4, and if the instruction counter is at the beginning, one moment please, let me check. I implemented it normally. well, we should technically we should subtract the length of the whole instruction, but this would not give us the right values anyways, I think. Let's quickly look to the code again, just to be on the safe side. So R8 is this, and we would have wanted it to be um 10. Okay. Why would that be 4? I mean, we can just add -4 and then later, so we see whether we get the right values, and then we check why it always is off by 4 and not by some more reasonable value. Disassembly, call here, run. Okay, now we have the values we wanted, so if we go with R8, let's not quite right, R8 plus 8, yes, this is fine, and R9 should be just a void stern, which is 0. Okay, so these are correct, and now let's see. This one probably will not be. Nor x. Yeah, that just points somewhere. Wait, no, that's that's right. 8 should be good. Our code starts here, and at 8 we have the offset of the function we want to jump to. Okay, so let's just make a step. Yep, that worked. We are where we wanted to be, and if we now continue, then we already have our injection working, and now we run into the next breakpoint. Okay, let me think. Why do we need to add 4 everywhere? That is unexpected. Path offset, because this already was incremented. No, it was not incremented. It was, but it was incremented by 3, and here it was only incremented by 2, and it's always 4, which we are off. I think about that later. Let's, since it's working, whether our path offsets are wrong. No, they look correct. This is dynamically computed. It looks like we are always exactly off by the length of the data type that we want to add. Does that make sense? Yes, it makes sense. It makes sense, because what we would want this number to be -7, or rather +7, but here we already add 3 to it. But then the question is why this actually worked. No, sorry, here it also worked because here the length of the instruction is shorter and we only need this. Okay, so let's just since we are using it always this way, let's just modify base. So we have minus base, just edit -4 here, so that this will give us always the right offset. Or I could also not write 4, but I could also write size of word, size of word. Okay, that makes sense. Okay, so we also, as far as to have our injection working, since we are already over time, we will skip the calling of a internal function. We will just clear the stack and restore the registers. So let's see. We have the function here. So we with our stack here, we just change this to an add. Assembler. So how different is that? Actually, we should maybe save those bytes as well here, and add. Oops, that was a mistake. Assembler. So as we see, we only change here within the instruction from EC to C4, and the rest of the instruction stays the same. So EC to C4, EC to C4. Yes, and this is then add. And now we want to restore the register. So for and in gleich Function ist kleiner no, we want to go the other way around in reverse. 0.0f y e is greater 0 I minus minus. Oops. And now again we need the same skip for the RSP, skip RSP, and then we will need our instructions. So these were these ones. So we have the same prefix if we are greater than 7, and else we just add what's the instruction now? 50 0. Yeah, I think so. 50. And E and no XF and no X7. Let's do the right thing. So it will write from the end, from the F. It looks like it's a 51 to me. Wait, let's just write pop rax and see what we get. We get the 58. Yeah, that makes more sense. 58 and then this. That looks fine. Okay, so this should work, and then we need the this one. We can copy it from here. It's to restore all the floating point registers at once. Over here the next stack. Okay, Streitpunkt. So we have restored everything, and then the only thing we need to do is to jump to our jump location. So we want something like .mp rip plus something null x this comes to this. Okay, so can copy. So here we have 25 FF, and it's not the loader offset but the return offset. And that's it. That should work. Let's try it. The second breakpoint should never be reached, ideally. Okay, injection successful. Why did it crash, or is it doing something? As our test step runs in an endless loop here, so let's put the breakpoint. Yeah, so actually it's working. So let's just comment out this endless loop, and now we'll get the injection successful, and then we'll get the rest, and of course the breakpoint. So injection successful. Then we have here our other code. The program works, so the injection does everything as it should, and we are just 18 minutes over time. So now if we would want to do more things, then here would be the right place to do it. Here we could call get pros address, and then or rather call loader, and then and it would be act the same way. We would save the address which this returns to a new slot here somewhere. We would I think again need to provide the function name as a Unicode string, even better as a ANSI string, which is similar. It just uses chars instead of vchars. And then we could call the return function address directly, and then enter an arbitrary function within our DLL before we return the control to the original control flow. Okay, so that much about code injection, more advanced code injection techniques. As we have seen, it's really easy to screw something up, and hence it is good to try to write the code as incrementally as we can. Another improvement that we can do is that we could actually save the path somewhere into this larger code area, such that we have only one code block which we write to our application, to our target application, but this method is fine as well. Any questions?
Maybe a bit stupid, but what we just wrote is in some sense quite specific then to x86 processes, or like if you would switch to ARM, you would need to rewrite everything. Or
yes, of course.
And is it, or that's clear, but is it also even CPU architecture specific? So because there might be some registers which are...
Well, of course, the whole shellcode is specific to one selected CPU architecture. So even if you change between 32 and 64-bit on Intel, you would need to rewrite good portions of this. So,
but it is the hooking is also used commercially, or in that sense. If you is it also used, for example, to have overlays in games that you hook into some drawing function or stuff like that?
Yes. Exactly.
So these poor developers really have to write the code that bulletproof then for
yes, I mean it's even like you if you want early process execution, then you have to even take into account that some of the functions you want to hook may already be hooked by some other tool. For example, a lot of anti-malware tools like I don't know, asset security or any or Kaspersky. Okay, Kaspersky nowadays should not be used probably, but McAfee, which always was shit. But all of these security tools use such techniques to be able to manipulate the processes on the system. And for example, monitor selected function calls.
Yes.
Generally, what you would do, ideally, you would try to, when possible, just for the DLL injection, use the create remote thread with load library, because this is kind of foolproof and except of the problem of getting the right address of your load library function, architecture independent. And the nice thing about the load library V or A functions is that they just take as argument one address where the string just has to be which they load. The underlying NT DLL function, the loader load DLL, this one, is in that sense much less user friendly, as it requires us to provide basically a couple of arguments, which cannot be done with the simple methods like create a remote thread, or even with the ALPC Q user ARPC. Those only can pass one argument, so you need you cannot do these tricks before the kernel 32 DLL has been loaded, but usually this DLL will be loaded very early in the process lifetime. One thing that probably is used most commonly is hooking, like we did here, where we have a process starting up, and what we are hooking is the first thread within the process, because we know that at this point the NTDLL has already loaded all the needed kernel 32 DLL and other DLLs which are required by a program. So for example, if we are running a 32-bit process on a 64-bit CPU, then we would need a WoW64 and WoW64 Win DLL to be loaded already as well, and the NTDLL does all those things. So this hooking method is at least somewhat easy, because you can create much well, you can use much simpler shellcode. You don't need to do it as we did currently with the anti-load, with the using the NTDLL function loader load DLL, as it's called. The reason why we would want to do it this way is if you would want to intercept the execution before pretty much any DLL is loaded. So what we could do, for example, is we could hook the function loader load DLL from the NTDLL, and then during the very early process initialization, when the NTDLL tries to load the kernel 32 DLL, then the code execution would be detoured to our code. But this would complicate a few things, because we of course then from our code could not call the original function, since the function then is well broken. So what we would need to do is before we call it somewhere here, we would need to restore the original function content. So we would have a detour that jumps from the function to our shellcode, like we did last time with the message box. Then here inside we would have somewhere in our payload section here the original bytes that were in the prologue of the LDR load DLL function. We would restore those. Then we would make load DLL on our own DLL, and possibly we even might want to first actually make a load call to load the to the kernel 32 DLL, and only then make the load call to load our own DLL to ensure that the kernel 32 DLL is already loaded. But this strategy would allow us a very early process execution control. So this is what most security tools would try to achieve one way or the other. For game overlays, I guess they are just going with create remote thread, because then they don't need to write any shellcode. And for the hooking of functions as such, as I said the last time, there are a couple libraries out there which you can use. And using those libraries is quite trivial. You just are calling a function that is, for example, called hook function, and then you are providing the address which function you want to hook and the address with which function you want to detour this execution, and then everything else is done by the library automatically. So the library will analyze the function you're trying to hook, create a appropriate a trampoline for the function, and return this trampoline to you, so that then you can easily work with it. I can show you an example of using a library. I have here a very simple loader. The only thing it does, it starts a process, and it ensures that the process, even if it started in a remote terminal session, will think that it started on the local console, which is highly useful. And the way this works, so we have here, of course, somewhere our injector. When they put it here, inject, which just uses the create remote thread method with load library A, and then inside our DLL we are including the min hook library. It's on GitHub available, and then inside our DLL main function we initialize the hook library, then we just create whatever hook we want to create, and then we just need to enable it. And this create function, you tell it which DLL you want to hook, which function you want to hook, then you tell it with which function you want to hook that. And last but not least, you get a pointer out here, which will be the trampoline to your original function. So you see that in our detour function, we check if it checks for a remote session. Okay, in this case it always thinks it's in a remote session, but we would normally want this to be 0. And if this is not the case, then we just call the trampoline, and we didn't need to write any own code or analyze the get system metric function manually. We just use the function. One thing to be said about this minhook library is that it is how say it, the way it operates is it does not analyzes the prologue of the function, but rather someone just did this once for all the known Windows functions and hard-coded a list of trampoline templates. So if you would want to hook some random function from a random library, this function could fail on doing that. If you want something that will work with everything always, then you need something like detours. Did I write it correctly? Yes. It is a library provided from Microsoft, and since version 5 it's open source and free. But this is version 4, but it should be already version 5. So detours. Let's see. Okay, so for some reason here in the releases the only linked one is the old version 4, but the code here is already version 5, because we also have already a disassembler for ARM and all the other useful architectures. And there are also some samples. Okay, there are a lot of samples. Let's open some of them. Maybe the Echo one. I have no idea what it does. So we have our main, we have main Echo. Hooking it somewhere. Yeah. Okay, so there is somewhere a function called real echo, probably in main. There's the function echo, echo null. That will be the real echo that does something, and then we have here in our injection example, it will resolve the function address, and here you have how to use it. So you say that you want to start doing something, then you tell detours the only thread which is allowed to run while the hooking is being done. The reason for that is that while you are writing the memory, intermittently you will be in an inconsistent state. So if another thread would try to call this function, it would crash. So what you do is you tell detours to more or less halt everything except, or rather you will be telling detours this thread must stay. Then you say where do you want to attach it, and then once you do this commit operation, then and only then it will stop all the threads and actually change the target function with the jump to your to your new function, and while doing that it will hold all the threads except the current thread. And then of course you are done. And you can also use this library to remove hooks. If you decide that you are done with whatever you were doing, then you can use this detach detours detach function to remove a hook that you have previously have installed. And there are a couple more libraries that do the same thing. What was it? Fancy hooks or something like that. I don't remember, but generally people either use this minhook library, which we can quickly Google as well. Minhook, yeah, this one. But as said, it is super small, but it's limited only to x86 and x64, so it does not support ARM, at least not yet. And given that the last change was 2017, it doesn't appear that the author is still active. But Detours, as being a Microsoft offered package, is, well, it's still 2 years since the last change, but nothing changed since then, so they didn't add new architecture, so there is nothing to change about that. But since it's now MIT licensed, it is a really good option and a very powerful one. Yeah, any other questions?
Oh, it's very interesting. I've actually never before the lecture heard about hooking at all.
Yeah?
I admit, yes, coming from Python, I mean, you're not so familiar with it.
Mm-hmm.
Yes.
Okay, so that's that. A lot of success with your exams, and maybe see each other at some point in future. Bye bye.
Yes, for sure. Bye bye.